My name is David Joyner, and I work for Udacity developing and teaching classes in the Georgia Tech Online Masters of Science in Computer Science program, or OMSCS for short. If you want more information about the OMSCS, I invite you to check out some of the other presentations we have here at Learning at Scale. For the purposes of this presentation, though, what you need to know is that the OMSCS program aims to give an authentic master's degree experience at a much larger scale than residential programs. This semester, we have over 3,000 students enrolled in the program, taking an average of 1.5 classes each. I teach a couple classes in the program, and I help other professors with their classes, and a huge responsibility of ours is detecting code plagiarism. With 3,000 students, even a small percentage of students plagiarizing is a large number of actual cases, and we need a way to detect those cases. In the past, we've used a system called MOS, for Measure of Software Similarity, from Stanford. MOS works like this. You have a set of student code files. You might also have some permitted code, like some boilerplate code or some utility methods that you would expect to be in some student's code. And you feed that all into MOS, Measure of Software Similarity. You upload it all to a server via a Perl script, you wait a few minutes, and then you get the results. The results are in the form of pairs of matching submissions, pairs of code, pairs of files that were found to have identical or very similar code. Part of this report are the number of shared lines, as well as the percent of code that's shared, and then it also provides an interface for easily navigating amongst the perceived shared code. Generally, MOS works quite well, but it wasn't designed with our use case in mind, and as a result, a number of challenges have emerged. First, there's the challenge of false positives. In our experience, about 50% of the pairs that MOS generates are actually false positives. Second, when we're working in this environment, we want to differentiate current projects and past projects. We want to test current students' code against previous semester's code to see if anyone got access to an older project, but we don't really care at that point about testing within previous semester code, because we would have taken care of that during the previous semester. But MOS doesn't have a way of filtering like that. It compares every file to every other file in the upload. Third, the majority of the cases of plagiarism that we see aren't simple pairs. You might have several people all collaborating, or you might have one previous semester project that's copied by a number of different people. But because MOS only works in pairs, it would show these 4 people as 6 distinct pairs of plagiarism, and it would show these 4 cases as 10 distinct pairs of plagiarism. And finally, the biggest challenge is simply scale. This semester, for example, in one class, we're testing 400 newly submitted projects against 1,200 past projects. And we're doing that for 3 projects per semester just for that one course. And we have over 20 courses. So the scale that we're dealing with is absolutely enormous. Last summer, I taught knowledge-based artificial intelligence in the program. During that class, I personally spent about 50 hours organizing code, uploading it to MOS, interpreting the results, and acting on the cases. That's a massive amount of time, and for not that many cases of plagiarism. And most of that time was actually spent on pretty tedious work. So one of my teaching assistants during that semester, Dana Sheehan, decided to fix that. For her class project in my educational technology class, she built a tool for addressing plagiarism at scale, or TAPS for short. TAPS is an extension of MOS that takes care of things like organizing code, filtering pairs, separating languages, and more. So now Dana is going to give you a description of what MOS TAPS does and how it works.
Thank you, David. To streamline David's process, I considered what the input looks like, what MOS needs the input to look like, what the MOS output looks like, and what we need the output to look like. For the KBAI class, student code is written in Java or Python and includes zipped and nested folders. MOS accepts unnested student folders, then outputs an HTML list of comparison links. The instructor only wants to see comparisons that include the current student submissions. David's challenge to find more than pairs can be partially addressed by creating a CSV file for results. Then at least he can sort and filter further as needed. Additionally, it would be helpful to provide a configuration file for options and remove the MOS limitation of running on a Unix platform. This brings us to the 4 design challenges for TAPS. Separate mixed languages into separate MOS submissions, flatten zipped and nested files for submission, filter the MOS output to remove unwanted comparisons and create a sortable CSV file, provide cross-platform support through pure Java. Let's see it in action. TAPS can be downloaded from GitHub in executable form to get started. TAPS works in multiple environments. This demo is run on Windows. The only constraints, initially, are that the current code projects be placed in one directory named current, and older projects in another directory named original. Student folders must be immediately beneath the project folders, but the depth of nesting for the student folders does not matter. The user ID and languages to include are configurable in the config file. We have an executable MOSTAPS jar called by a Windows batch file to get started. We see the upload status as the student files are submitted via queries. TAPS processes the project files, putting the flat folders together into an output directory and submitting to MOS. Once the query is answered, TAPS further processes the HTML results to create CSV files containing fields for lines and percentages matched, student names and projects, and the MOS pair links. Using a tool such as Excel or Calc, the results can be further sorted or filtered as needed. Code similarities can be examined using the MOS links, which are color-coded where similarities are present. TAPS was designed to streamline an instructor's workload when using MOS at scale to test for software plagiarism. It's a work in progress with lots of room to grow. Thank you for taking a look.
Using MOSTAPS, the tasks that took me almost 50 hours in summer 2015 now take me all of about an hour. And of that hour, about 30 minutes is usually spent just waiting for code to upload or download. MOSTAPS organizes the results in such a way that it's very easy to go through and filter out false positives by hand, as well as knitting together those webs or rings of plagiarism. The process has actually gotten so much faster that I've been able to take care of it for some other classes in the program. So thank you, Dana, for saving me an enormous amount of time, and thank you for watching this.